Welcome everybody to another UPAC Colloquium. In this case, we have the pleasure to have Professor Helge Kragh. He's an emeritus professor at the Niels Bohr Institute since 2015. He's an historian of science, has very extensive career, analyzing different epochs from the 19th, 20th century, the history of physics, cosmology, astronomy, and also chemistry. And in this case, he will talk about the story of cosmology and especially the case of antimatter. So,
okay, thank you. Yes, I'm a historian. As a historian of science, I'm not a practicing scientist. I was originally graduated in chemistry and physics, so I know a little bit of it, but I never done really scientific research, and not a philosopher either, although I have written something about it. Anyway, I'm going to give a talk about antimatter, and more specifically the role of antimatter in astronomy and cosmology. As I will say a few words about later, nowadays antimatter is a hot topic as a laboratory kind of science. When I looked at this problem, for various reasons, I found it interesting. One of the reasons being that I once wrote a big biography of Paul Dirac, and Dirac was, of course, the one who invented the idea of antiparticles. But it soon turned out that when I looked at what has been written about it, that painfully little has been written about the historical development of that kind of science. So I decided to do something about it, and which has very recently resulted in two articles. The one in Annals of Science is the most relevant to this talk I will give today. But before I come to antimatter and its history and its present status, I need to say a few words about the status of cosmology today, and say a few words about what usually is called the standard model of cosmology. There is such a standard model, just as there is a standard model in particle physics. This model is very often called the lambda CDM model, which and you all know about it, so I'll not go in any detail, but practically the large majority of astronomers and physicists believe in this model. I'll say that lambda CDM is something of a misnomer. I mean, it's true, of course, that lambda, meaning the cosmological constant, as responsible for the dark energy, is one crucial element in the model, and CDM, cold dark matter, is another crucial element. But it shouldn't be forgotten that there are other elements in that model which are older, because in a certain sense, the lambda CDM model is merely a refinement of what in the 1980s was called the standard hot Big Bang model. But then about 2000, we added the lambda after the discovery of the accelerated expansion of the universe, and people also realized that there had to be this cold dark matter, so that was added to it. I also just need to point out that what do we mean, or what do people in the business mean then when they call something a standard model? A standard model is a sociological label, more of anything else. It is simply the kind of model which the large majority accept as the best one. Not necessarily the true one, but if there is a very broad acceptance of a certain framework, then it is a standard model. That is the case in cosmology, It's also, of course, similarly the case in elementary particle physics. Well, most people agree that in the very early start, immediately after the Big Bang, taken to be time equal to 0, there was this inflation phase, which has been tremendously important, but inflation is still today somewhat problematic in the eyes of many people, at least. But I guess that the majority of people, they will say that, yes, there was an inflation phase. Inflation has been very successful in a certain sense, but there are also certain problems with it. More recently, this model has been criticized by a number of people, some of them astronomers, other people, philosophers, and it has been argued that cosmology is in a state of crisis. And when people claim that cosmology is in a state of crisis, they are typically referring to various problems or anomalies which the present model cannot explain probably, or doesn't take into account or something. And I'll come back, I'll say just a few things about it, and then I'll say more things about the antimatter, which can also be considered one of the reasons that at least the standard model is not perfect. But when people argue that cosmology is in a state of crisis, I mean, one should keep in mind what we mean by saying that a theory is in crisis. The notion of crisis may be and is typically associated with Thomas Kuhn's philosophy of science. Whatever is the case in this business is a non-Kuhnian crisis. There's no, I mean, sometimes people who are critical to this model, they say that we are in a state where close to a new revolution in cosmology. People love that term, revolution. Not only scientists, of course, and that we are in need of a new paradigm. I mean, concepts taken perhaps from Kuhn's philosophy. And if that is what they mean, there's no doubt that cosmology is not in a state of crisis. There's no real indication that in the future we will have a totally new kind of cosmology. And recall that according to Kuhn, one paradigm is incommensurable with the previous one. It's a very, very radical concept. And it's almost certain, and the large majority of cosmologists will agree that whatever will happen in the future, it will not be something totally different. One thing which can be questioned, of course, everything can be questioned, but evidently modern cosmology theoretically is based on Einstein's field equations in 1917. It's also based on the solutions to the Big Bang, to these equations which correspond to Big Bang models. And very few people will deny that there once was a Big Bang, and that the cosmic microwave background is solid evidence, almost a proof of this mythical event. But nonetheless, let me say just a few words on two of these problems. I'll not speak about dark energy because it's too big a subject to just say something reasonable about in a few, but I will say a few things about the dark energy problem, which in a certain sense.
I briefly asked when you said we shouldn't expect a revolution, is that because the nature of these problems are not such that they require overthrowing the paradigm or just refining it?
Yes.
Or is it because the model itself is so phenomenological and effective that it can kind of
No,
fit with error?
I'll say that it's the first thing. I mean, if we look at some of the events in the history of science which come close to the Kuhnian revolution, one paradigm succeeded another, such as the situation in Lagrange's chemistry, and things like that, then these two kinds of theories were so different that you couldn't translate concepts from the old theory to the new theory or vice versa. And that will not happen here. Dark energy, according to the modern standard model, I mean, the reason why it's called lambda CDM, this lambda, of course, is a symbol of Einstein's cosmological constant, which he introduced in 1917, and has had a very remarkable history. It's normally conceived to be the quantity which is equivalent to the energy density of vacuum, an idea which goes all the way back to the 1930s, and there's a very interesting story about that. I have written about it in detail. But when people at about 1970 were able to calculate or estimate the energy density of vacuum on the basis of quantum field theory, they come up with a number which was much too large. I mean, it's only fairly recently that we have an observational number for the cosmological constant. But the point is that this old problem, that the calculated value, the theoretical value of lambda, is ridiculously larger than the one observed. That has been known for 40 years or so. People have worked on it, and they have come nowhere. So this quotation by Weinberg, I should say, is certainly probably correct. I should also say, as an historian, that it's also probably or possibly apocryph. I try to, when a historian looks at quotations of this kind, and these quotations are normally without any source, and their suspicion is that they try to find a source for it, and I tried to and couldn't find it. Anyway, this is a problem. It's a recognized problem. It has been a problem for quite a long time. There are people, of course, who have come up with different versions of the dark energy. There's something called phantom energy, something called quintessence, which are related to it but are not constant. And they're all kind of ideas. But none of them are widely accepted. They are definitely minority views. Then more recently, and certainly today, there's much talk about what is called the Hubble tension, a very interesting phenomenon, which is, in a certain sense, is simple, because the Hubble constant, or what officially is called, or should be called, the Hubble-Lemaitre constant, according to the International Astronomical Union. This constant, I will call it a constant, but of course it isn't a constant. It's a parameter. By its very nature, because it's a measure of the age of the universe, so by its very nature, it changes in time. But people still call it the Hubble constant, and why not? It's a fundamental constant and has been that since Hubble's days. And it should have a definite numerical value. And the problem is that people can determine the value of the Hubble constant very precisely nowadays. But unfortunately, when it's determined in one way, it doesn't give the same answer as when it's measured in another way, you can see here, it's approximately 70 in this awkward unit of what is it, kilometer per second per megaparsec, a very strange unit, but yeah, anyway, so this is what is called the Hubble tension. I have also included in here a historical a graph of over a very longer time, which I thought is interesting. The first one who estimated the Hubble constant actually before Hubble, that was Lemaitre in 1927. Here we have Hubble's values, and you can see they are about a factor 8 to 10 times as large as we saw. And then comes the period which is sometimes called precision cosmology. I mean, where people actually were able to determine the cosmological parameters very precisely. And there isn't a whole lot of difference between these two numbers, but still they're different. And that's intolerable. It's hard to say today whether this is a genuine problem or whether that it will disappear in due time. I mean, it's quite possible that in the future, maybe a few years from now, people will agree on a definite value. But there are some people who take this to be a sign of crisis. But let me go on to what, after all, is the main subject of my talk, namely antimatter. Today, as I indicated, antimatter is a hot topic of research. People have looked at antimatter and they have produced antiparticles to some extent, very, very simple antimatter in the laboratory. At CERN, they are very occupied with this kind of work, also at some of the other big laboratories, of course. So very briefly, the anti-electron, 1933, I will say that it was discovered. Then, of course, called a positron. Then we had the anti-proton, which was discovered, but in a different sense, namely manufactured in the laboratory, 55, and so on. But notice that the most complicated anti-atom ever found in nature, or produced in the laboratory, is anti-hydrogen, or maybe the anti-helium nucleus. But people have not been able to manufacture a single helium atom, anti-helium atom, I mean. And of course, there are no anti-molecules produced. So, in other words, to call it an antimatter factory is a gross exaggeration. They're not producing antimatter, and probably they will never do that. But in principle, of course, it should be possible. And if you invest enough money and enough resources, then it should be possible to produce an anti-uranium atom or anti-water or what have you, and why not an anti-human? So that is, physicists consider this very important. And they have, of course, produced some interesting results. For a long time, there was a lot of discussion of whether antiparticles act gravitationally different from normal particles. Anti-gravity. Does an antiparticle fall in the gravitational field like an ordinary particle does, or does it go the other way up? Now it's almost completely certain that there is no difference, gravitationally speaking, between matter and antimatter. But let me go back in history and point out that there is a kind of prehistory of antimatter. but that is, I just mentioned it, it's really not relevant, but it's sort of fun nonetheless, that one can find the idea that the names antimatter and anti-atoms in 1898, when some people speculated about it in a totally different framework, of course, because the modern idea of antiparticles or antimatter is very much a quantum phenomenon. I mean, it wouldn't exist without quantum mechanics, of course. And the short story is that, you know, in 1928, Dirac produced this marvelous Dirac equation for the electron satisfying special relativity. And there were certain negative energy states which he tried to interpret physically. At first, he thought that these negative energy states of the anti-electron were identical to protons, which was a very good idea, except that it was completely wrong, of course. But in 1931, in a really marvelous paper, he realized that the anti-electron, the positively charged anti-electron, must be a separate particle, a particle by its own right, so to speak, and he called it an anti-electron. This paper is really an amazing one, because Dirac only introduces the anti-electron very shortly at the end of his paper. It's about something very different. It's about the prediction of magnetic monopoles, where he argues that there ought to exist in nature magnetic poles, and he proves that these poles are allowed according to quantum mechanics. But that's a different story, although it's also related to cosmology. So there we have the idea of antiparticles, namely the anti-electron alias the positron. A couple of years later, after he was awarded the Nobel Prize together with Heisenberg and Schrödinger in 1933, and in his Nobel lecture, at the end of this lecture, he speculates about antimatter. And he's the first one who uses the term as we use it today. He says that he speculates, of course, and he knows that it's a speculation. Perhaps there are stars built up mainly of positrons and negative protons. There may be half of the stars of each kind. So here we have the suggestion, or at least the speculation, that that antimatter is as abundant as normal matter. He also points out that we cannot find out whether a star is made of matter, of antimatter rather than matter, by observing it, meaning investigating its spectrum, because the spectrum will be precisely the same as that of matter. And he also realizes that there is, in principle, the possibility that we will travel to the anti-star, because then we, or the instrument, will annihilate with the antimatter in a huge explosion. And one might imagine perhaps that such an interesting prediction, that it caught a lot of attention among scientists and non-scientists, but it didn't. So Dirac's idea of antiparticles was by and large ignored by the physics communities and also by the astronomers. It took a very long time until physicists began taking the idea seriously. But in the meantime, other people of a very different branch, science fiction authors, did take it seriously. In the 1940s, we have in American science fiction stories, people who are writing about antimatter. They are using a different name, which is obsolete nowadays, and you probably don't know it, contraterrene matter, meaning matter which is contrary to that on Earth. But that's simply another term for antimatter. And so we have to go to the mid 1950s, and the basic reason why people slowly began to warm up to antimatter was, first of all, that in 1955, as I said, the people in America produced antiprotons. Shortly later, also the anti-neutron, and a little later again anti-deuteron. All this made in the laboratory at high energies, of course. And the other thing was that Dirac's idea that to every particle there ought to exist an antiparticle. The charge conjugations, or charge inversion, as I said, got justified theoretically, and at approximately the same time we have the what is called the CPT theorem, the most fundamental theorem in physics, any kind of physics, and that was accepted. Of course, it's accepted still today, etc. So it was only about that time that a few physicists, not astronomers, but a few physicists began wondering, where is the antimatter? Because theoretically speaking, there ought to be antimatter, and apparently it wasn't there. So there must be some reason why it isn't here, and that is still the situation. One can identify three different answers to the question. Yes, namely these three. First, one might, because not any longer, but certainly in the 1960s and 70s, it made sense to postulate that there are anti-stars, there are anti-galaxies in our universe, in the observed universe, but they are very far away. And of course, we cannot determine whether a certain star is anti or not. But at that time, two Swedish, very notable Swedish physicists, Oskar Klein, who you definitely know about, and his younger colleague, Hannes Alfvén, proposed what is sometimes called plasma cosmology, and an alternative to relativistic Big Bang cosmology. It was taken quite seriously for a decade or so, but then it was abandoned, and today it hardly exists any longer. But this idea built on the assumption of large areas of in space of antimatter. One of the reasons why this theory didn't survive was that it couldn't explain the cosmic microwave background discovered in 1965. People tried to do it, but they failed completely. And so their idea of a symmetric universe, meaning symmetric in electrical charges, is not any longer viable at all. So we can. It's only historians who are interested in this. All other people can forget about it. But there are other ways of thinking of a symmetric universe, namely by, again, postulating or suggesting or speculating that at the birth of the universe, at t equal to 0 or plus minus very small time span, our universe was created consisting of matter, but at the same time, another anti-universe was created, so that the universe and the anti-universe were created in pairs. And that idea goes back to the 1950s, basically an American nuclear physicist by the name Morris Goldhaber, and I will come back to it in a few minutes because this crazy idea, I mean, it is sort of crazy because there's no observational evidence for this anti-universe at all. But it's not a dead theory. There are people working on it still today. However, the standard view has been for a long time that our universe is not symmetric, is asymmetric. And the asymmetry is produced, can be sort of explained by nuclear or elementary particle processes in a very early universe. So that according to this idea, which is a standard idea today, the universe was born symmetrically, as many antiparticles as particles. But very, very soon after t equal to 0, something happened, and the antiparticles were suppressed, and the rest of it is a story of particles and not antiparticles. But let me say a few words about this. I said it was a crazy idea, but not sufficiently crazy that it might not be true, of course. But here we have this idea of two completely symmetric universe and anti-universe. Of course, if you live here, you would call this an anti-universe and change the names. In the way that this idea was proposed in the 1950s and 60s, it was purely speculative. One of the problems of this kind of models, here we have a more modern version of it, but one of the problems is evidently that how should we know about anything empirically about the anti-universe? It's the same kind of problem which turns up in ideas of the multiverse, because by all accounts, the hypothetical anti-universe is causally disconnected to ours, meaning that we cannot possibly get any signals from it, and so people have to appeal to other ideas in order to justify it. I said that it's not a dead idea. It has turned up several times, in fact, during the last decade, and it's not only speculators and cranks who are fascinated by this idea of an anti-universe. I mentioned one article only a few years ago. Many of you will be aware of the name Neil Turok, a very distinguished theoretical physicist and cosmologist who had done some very important work. He's employed at what time was the director of the so-called Perimeter Institute in Canada, which is a premier institute of that kind of very theoretical physics and cosmology and things like that. So he's a very distinguished author, and his two co-authors are equally distinguished. And also notice that this article is published in Physical Review Letters. That is one of the most prestigious science journals ever for a physicist to publish in. So it has been reviewed critically and so forth, for people have decided that this is interesting and so forth. But when one reads this paper, it's obvious that it is throughout theoretical. It's very hard to justify or to come up with empirical arguments, observations, or experiments in favor of this anti-universe. So what we have is a theory which, of course, explains why our universe is asymmetric. It also said that it explains dark matter. And the authors are very keen to emphasize that this is not a speculation only, it is testable. of course, to the word testability is a mantra among physicists, because if a theory is not testable somehow, then it doesn't qualify, according to most people, as proper physics or even proper science. Testability has always been, of course, a code word in science, but it's also typical that they do come up with some predictions. And one of the predictions, for instance, they say that if gravitational waves from the very early universe, primordial gravitational waves, are detected, they haven't been detected yet, and if these are found to have long wavelengths, then it will falsify our model. To say that a model is falsifiable is rather stronger than saying that it's testable, but of course it's part of it. And it comes up with various other predictions. A good theory evidently has to be not only explanatory strong, but also to have to be predictively strong. But none of these predictions are realistic. To go back to the standard view of most people, namely that the present asymmetry of the universe is the result of symmetry breaking processes, nuclear processes in the very early universe. This idea goes right back to the famous Andrei Kragh. I'm going to say that he's famous. It's not because he was a great physicist, which he was, but for other reasons, political reasons. He received, as well known, the Nobel Prize for Peace. Couldn't receive it, but so he wrote this Russian paper in 1967. Nobody really read it, in the West at least. So it took quite a time before the idea became probably known. Here we have a citation pattern, and you can see that it takes many years, and today it's cited all over. And Sagarov's idea, at the time he couldn't tell what kind of processes were responsible for the symmetry breaking. But in the 1970s, 80s, so-called grand unified theories were very popular. And grand unified theories can do something that ordinary theories of particle physics cannot do, namely that they can they have processes that do not conserve the baryon number. The number of baryons is an invariant according to standard physics, but not according to grand unified theories. So one might speculate, and people do speculate, that in the very early universe, and we are speaking about extremely early, before 10 to the power minus 35, I mean, perhaps there existed a number of so-called X particles, X bosons, and they have this, they can change the positive to negative baryon number in theory. One of the problems is, of course, that these X bosons are totally hypothetical. They're very, very heavy, and nobody thinks that they ever will be detected. And there are other predictions from grand unified theories which have also not been verified, especially that the proton is unstable with an exceedingly long half-life. So I think today that grand unified theory is more or less dead. And that means that there's still no good answer to how to explain the original asymmetry of the universe. The problem comes up from time to time, and all kinds of strange hypotheses have been suggested in order to explain it. If we are not allowed to use grand unified series, and one is not today, then perhaps neutrinos may provide an answer. You're probably aware that in the late 1990s, people discovered that neutrino might oscillate, as the term is, that the three different flavors of the neutrino can change from one flavor to another. Electron, muon, and tau particles. And in that way, it is possible to imagine that something of that happened in the very early universe. But again, these kinds of ideas have not been verified to any extent, and they still rely on hypothetical particles outside the reach of laboratory physics. I will end with locating this problem. I don't know if I said that explicitly, but now I do, that the antimatter problem is remarkable because it is old. People have known about it for 60 years. And they have come up with numerous attempts to explain it. And all these attempts have failed. That in itself is not a sure sign of crisis. There have been earlier examples in the history of science when we have unsolved problems which has remained for decades, and then people have been able to explain it. So it's still possible, of course. You all know undoubtedly about the venerable principle of plenitude. Going back, well, either to Plato, or doesn't go back to Plato, but certainly to Leibniz, who was a great fan of this plenitude principle. And in his very various versions, they say that what is possible is real. Anything which can't be the case is the case. So did God will it. It had played a very, very important role in the history of science, not only in the biological sciences, but also in physics. For instance, when Dirac in 1931 postulated that there exist, or suggested that there exist magnetic monopoles and there exist positive electrons, he didn't know about the plenitude principle, but he formulated his suggestion in quite the same way as Leibniz had done much earlier. But it's evidently a problematic principle. First of all, one has to take into account what does exist means. In the old days, things which existed in nature. I mean, where else should they exist? But nowadays, of course, there is a possibility that they exist in the laboratory only, and perhaps only for a split second. Does it still mean that something exists in the same way? I mean, and there is the element of time. When we say that something exists, that is present. That means literally that it exists now. But what if something existed in the far past, but doesn't exist any longer? Would you still be able to say that it exists, or instead of saying that it had existed? So there are all kind of, one should specify what it means. From our point of view, of course, possible means that it is physically possible. And antiparticles and antimatter definitely are physically possible. They are not only imaginably or logically possible. But that is the situation, to the best of my knowledge, as it is today. And undoubtedly, people will continue working on this problem. It's impossible to say, of course, whether they will come up with a a good answer, and a good answer means an answer which is acceptable to the majority of people working in the area. Yeah, that's what I have to say about that. Thank you.